And then finally, we are going to look at what is the essentially the sort of the newer things, which is the GPT-3 chat GPT type thing. So I'm just going to wait for a couple more minutes, and then I'm going to start, and I will share my screen. And by the way, now also now I have to reshare with you all the documentation where it is. I'm going to share this with you the same place as it was last time, but now that there are some more new people, I'm going to have to share this link here. Let me do this now. Uh, okay. Just make sure that I can share this. Okay, Kaji Marathi AI workshop. Uh-huh. Okay, so this is where all the slides are kept. Yes, and including today's slides, last time slides, and of course the video is being emailed to you. The recording is being emailed to you by Anand directly. So I don't have the recording, but all the material which I'm using, including my slides, including the reference material I have put in, which includes FAQs, two books, one cheat sheet, things like that, glossary, all of that is in the same place, including the sessions for today. So this is the basic idea of the session today, and I think that that's where we'll have to do this. Now it's a little bit confusing for me because I am going to have to sort of recap everything which I did last time within a relatively short time, but I think that's still worthwhile doing, mainly because there are a lot of people who are new, and I think that if you don't understand this session, then I think the next one will be even more, because then we are starting the coding side. So I think let me now quickly recap where we are at with that. So
Can
now
I
I'm
make
going,
one more
yep,
small request?
yeah.
Doesn't have to be addressed now. Since there are these people who have specific interest in AI, maybe worthwhile to have kind of a group email contact available, something like that for internal exchanges. Um,
Yeah, that's actually a good point. I think Anand, I will ask this to Anand actually.
yeah.
I mean, the main thing is that here there are at least 3 or 4 institutions. So the full group we have is quite large, but I'm quite happy to. Yes, so today we've got about 16 people. Last time we have 25, but the number of people who have registered on this are about 100. So this is what I'm not sure about, if somebody is not getting the message entirely, or what, because that's the confusing part for me. But I will happily share this. I will speak to Anand and I will do that. Perfect.
Mm,
Okay.
thank you.
Thank you. Thanks. So now let me go back and start the presentation. What I'm going to do, like I said, I was in any case going to do a recap of what we did last time, because I think that is essential to sort of understand what we are doing, just for the revision sake. But in this case, I think have to do it because there are some more people who are new, and I think that they would really be completely lost if we didn't do this. So what I'm going to do now is I'm going to quickly, and again, just to recap to everybody, that I have shared all the slides in the 1 minute. Here we go. Foundations, yes. Okay. So what I did last time in the first session was I went through the overall foundations of AI. And this was very important because it was very important to understand what we are trying to do before we do it. And so let me now share my screen. Yes. And it's my whole screen. Yeah. And I will wait. Okay. So now I'm sharing my screen. Yeah. And let me just quickly go and see. This is that. Okay. Mhm. Okay. So do you see my screen now? Foundations? Yes.
Yes.
Okay, good. Thank you.
Yes.
Yes. Yeah, good. Thanks. So what I'm going to do now is I'm going to quickly go through the sort of recap what I did last time, and I was going to do that anyway, like I said, because it's a good practice for us to really understand what we're doing. So what we are doing here is, by the way, here again you have the video link and everything else which Anand has been sending, and also there are some links to these things such as the glossary, the books, and things like that. Um, And so if you just let somebody in, because I can't let people in when I'm presenting. So that's the thing. And also these are the coding notebooks which we are going to use in the course. They're all linked here in my presentation, and all the slides will be also available with that. So all this idea is here. Now the overall idea for this course, if you have understood that there is the new thing called ChatGPT and GPT-3 coming along, and the overall idea is that we are now entering a new phase of AI, which is led by what I call copilot led. Yes, so copilot first development idea. So what that means is that for the first time, we are able to bring in non-developers into AI. And that's because you have something which is going to assist you to develop the AI. And what we are trying to do is, this is why this session is open to anybody who is even a non-developer. And the overall flow is that we are having the non-developers, i.e. the domain knowledge experts, design a testing strategy, and the developers working with them to actually test AI. So the idea is that both of you should be able to speak the common language of how to test a particular AI application. And in doing so, you are also going to learn in that idea. So, and of course, half of it is also be based on the ChatGPT idea, which is there as well. So there are 6 sessions, and the first 2 sessions, and we are in the second session now, is based on the foundations. The session 3 is by my colleague, Dr. Carter, and she's going to talk about the coding. Session 4 and session 5 are by me and my colleague, Aisha, and we are going to talk about GPT-3, basically how that works and how you can build applications using GPT-3 and what are the issues with that. So we are working very closely with Microsoft on some of these ideas. So I think that's where it's coming from. And finally, in the sixth session, you will be making some presentations about what you have learned. And this is really about how you can test AI, really. So this is the whole idea of the course. And in that doing so, you will learn hopefully quite a few things with that. All the class materials are in this link, which I have shared in the chat, including my sessions, my slides now. Yeah. A little bit about me, I won't say too much. So I am basically the course director at Oxford. My colleagues, the 2 colleagues I'm also involving, are also from Oxford. And of course, we'll use English, although this is the Gajje Marathi session, because they're not Indian as well, basically. So all of us are basically based in the UK or Oxford, and then that's how we build this thing. This is more diversity. We are trying to include everybody and things like this. So I will sort of skip these things forward. You can have a look. The key idea is people want to learn AI. So that they can sort of develop and get their skills. The mindset, what we call about with learning AI, is what is basic, these matryoshka dolls, meaning that you learn something into deeper and deeper ways. So AI is such a complicated subject that nobody ever understands all of it, and that's perfectly fine. It's a matter of sort of using what you know and applying to the problems that you have at the moment. Yeah. And the other thing about AI is there are
People
really
waiting to
three.
join.
Sorry,
People waiting. There are people waiting to be added. They're in the
can you
waiting.
just okay them? Can you okay them?
So I'm not able to do that. But
Okay, I was afraid of that. So now I have to stop and I have to okay. Okay. So now I have okay. So now I have to go back to do this. Uh-huh. 1 minute. Okay. So we were here, yeah. And what I was sharing here was the idea that there are really three titles in AI, which are the data engineer, data scientist, and DevOps engineer. And these are titles are typically in a larger company, meaning that there are 3 different job roles and you're doing the 3 things. So the data scientist is the person doing the algorithmic side of AI, and the data engineer is the person who brings the data to the data scientist, and the DevOps person is the person who creates the sort of puts it in a Docker container and productionizes it. But primarily the focus for us is the data scientist. Yes. And there are certain things which the data scientist has to do. And these are sort of areas which I go with that. Now, to recap, the main definitions which I want to use are machine learning, meaning that you are explicitly training an algorithm. Deep learning, meaning that you use automatic feature detection, which I will come back to this. AI, meaning artificial intelligence. Narrow AI, meaning what you are seeing today, which is mostly in the sense of AI for specific problems. And general AI, meaning that it's more like the Terminator movie, meaning that you have AI which can operate in any given context within there. So this is the general flow of AI, meaning that you have training data, you have a data set, you have a model, and you have a prediction based on the data set with that. This is how it looks like into a little bit more detail when you do neural networks. And when you do a neural network, so what you're looking at here is these are a series of neurons, artificial neurons, which are sort of mimicking the human brain. And you take a lot of images of something, and through this we effectively um, create whether it's a cat or a dog or a raccoon or something like that. And when it's trained, you show it an image which it hasn't seen before. So this picture of the dog at the bottom left is not in the training images, and then you sort of run it, and it identifies what it is, which is in this case a dog with that. So that's the general idea. What that means is that when you train something, the neural networks have connections between the neurons, as you can see here in the green one here. And therefore, the next time you show it something which it hadn't seen before, it is able to identify what that object is. So this is the sort of philosophy behind that. AI people get very excited about things, the job losses and so on, or they think that it's going to take over the world. But in a practical sense, it's very straightforward, and this is why I keep to these particular definitions, which are very specific in terms of that. Now, there are specifically some problems where AI is good for, and they include problems which are very large, problems which are open-ended, problems which have hidden rules, hierarchical rules, or are generative and things like that. So there are certain examples which I will come back to them with examples. And the other thing is to remember is that in traditional programming, you have the data and the rules and you get the outcome. And in AI, what you do is you get the data and outcome, and through that you find hidden rules. So the objective of this idea is that you want to find the hidden rules behind something. So this is the general principle of that. Um, so the basic flow, like I said, is you get the data, you clean the data, you explore the data, and then you effectively model the data and you interpret the results. When I say model, that means you train the data using machine learning or deep learning algorithm based on some data, and through that you then interpret the results of something which it hasn't seen before. So that's the general flow with that, and this is slightly more nuanced definition of that flow, which is what we are seeing here with that. Now it gets more complicated because AI has a number of domains which are connected, which include the mathematics, it's sort of linear algebra, statistics, etc. Then also the computer science, which includes the sort of the Hadoop, the columnar databases, and so on. You have multiple data formats, you have multiple modalities like the cloud and the edge and so on. And then, of course, you have different things with that. So if you look at machine learning, the basic idea of machine learning is that you have a series of algorithms, and these are the main sort of easy to explain them with a series of images, and they include classification, regression, anomaly detection, clustering, etc. Um, so that's the basic idea with that. Okay, so can I just maybe we take some questions now? Yes, I still have some people who are coming here, so I need to keep going inside and present them. So any quick questions at this point? You can speak up, or you can post something on the chat. WhatsApp group, yes, I think I can ask Anand about this, and quite happy to create a WhatsApp group from there. Yeah. Okay. Any more questions on this so far?
So one question is, because AI has come in, no one will lose jobs. But don't you see Microsoft, Google, Facebook, and all of them just throwing people away? These are people who have the programming skills or browsing skills or the development skills. So
Right.
don't
So
you?
there are a couple of things here. The first of all, I do believe AI will causes job losses, 100%. There is no doubt about that. The main reason for that is because any machine learning process is able to model a physical process, and the moment it does that, you can replace it. You can think about how you can automate some of that. So that is the first point with that. The second point is specifically the job losses in Google and Facebook and Twitter, etc., have two or three problems. Twitter is, of course, a different case with the Elon Musk problem. But specifically, Google and Microsoft and all those people recruited a lot of people in the pandemic, and that has caused the first problem. The second problem is that even there, the redundancies are mostly in the development people and not in the AI people. So when I say people who know I mean people who they know algorithms basically, so they can do some sort of a classification, regression, and so on and so forth, or they have worked as a data engineer, or they have worked as a DevOps engineer, working with machine learning models. And those people definitely, as far as I know, are not being made redundant. I think most of the job losses in the US have been more on the development side, certainly in areas like Internet of Things, augmented reality, virtual reality, all the bit about the metaverse and so on and so forth. But the traditional AI is still quite strong. But the traditional AI is different from a developer perspective. I hope that helps. Okay.
It does, and I do agree because what I see is a wave of change.
Yeah.
It's yeah, just like in the olden days when they found the motorized wagon that could lift
Yeah.
heavy load.
Yeah.
The people who used to carry those loads were made redundant.
Yeah.
So this is kind of like that. You have
Correct. Correct.
the ability to carry much more load using a much smaller set of developers, data scientists, maybe.
Yeah.
So you you focus, you refocus and re-energize your ways to focus on that aspect.
Yes. Correct. Now I think that one of the things which is going to be even more complicated is the bit about this thing about ChatGPT. And that's where we are going to look into the whole idea of generative AI, which we in the last two sessions, well, the third, or the fourth, and the fifth session of this course, because I think that has been a game changer, and it will completely change the rate at which things are moving into so many new types of areas. So I think that we are still not sort of. Uh, uh, Not sort of early stage from there with that. Okay, good. So there's another question here. Is AI dangerous for human civilization? Said by Stephen Hawking. Yes and no. I think there are risks and issues. Remember that all we are talking about right now is what is called narrow AI. The risk what he's talking about is general AI. General AI is basically the sort of the idea which AI can be autonomously operating into different areas, and that risk is generally at least about 20, 30, 40 years away. So I think this is going to be a risk, but maybe in the future. Okay, cool. Okay, thank you. So I'll go back to the presentation now. With this, let me just see, because I just don't want to break my flow. This. Okay. Okay. So the point here is that the basic idea of machine learning, as you have seen here, is classification, regression, clustering, and things like this. So that's the basic idea of machine learning. Now, the learning in machine learning is basically involved in learning a function. The learning a function is the same idea as what you learned in mathematics. So if you look at this equation of a straight line, y equals to mx plus c, uh, the idea here is that to find the best fitting line, you find the least sum of squares, and you minimize that so that you get the best fitting line. But this function on the right hand side is far more complicated. It doesn't seem to have any discernible pattern, which you see on the left hand side. So the idea here is that if you are able to model this using a series of neurons, then you are able to understand the behavior of this function just like you do on the left hand side. And that's the power of deep learning, because the deep learning idea basically is a series of neurons, and those neurons are able to model any physical activity within any physical function, given enough depth of the neuron. And this is the power of deep learning to a certain extent. And a function can be really anything with that. And as I said, that is the same idea of the mathematical finding of what is the function between two domains, function of x mapping from x to y, and we're trying to find out something which maps there. The challenge here is that the equation on the left hand side is very easy to do, equation on the right hand side is very hard to do, but it is still possible to sort of find out what this equation is from there with that using the neural network. Now I want to share with you one more thing here, is that is basically what are the types of algorithms. There are a number of types of algorithms which are basically supervised learning, which means you train it using some data. Unsupervised learning, like clustering, where it tries to find out a hidden pattern within data. And then you have semi-supervised learning, which is things like GANs and generative adversarial networks, etc. The way you group algorithms is by similarity, meaning that they are similar to each other. And then you have regression algorithms. What we saw before was fitting a straight line. You have classification algorithms, like you sort of classify two sets, and in this case you have this line which separates or demarks the red circles from the green crosses. And if you have a new data point, which is the blue one here, it falls in with the red circles. And this is the idea here with that. So you try to find out the best fitting line which does that. Then you have instance-based algorithms like K and K-means. You have regularization, which is something we'll talk about later on. We have decision tree algorithms, we have Bayesian algorithms, we have clustering, we have association rules, and so on. So this is the general sort of a grouping of algorithms within that. And then what you do often is you ensemble algorithms, meaning that you combine different algorithms together, which is what you often have to do to get the best result from them. And then there are certain new algorithms like reinforcement learning, which is what is the best example is what is used in DeepMind. Then you have semi-supervised learning, which is GANs. The best example of GANs, generative adversarial networks, is the fact that they are used in things like deepfakes and things like this. So that generally sort of covers the basic idea of algorithms. And then what you have is you have something which is essentially the basic idea is that you're given a set of features about something. So you have a given house prices, you are given a set of features about the house prices. You're trying to predict the median value of the house. Similarly, you're trying to find out the salary of somebody given their skills and their country and their years of experience. So given historical data, you're trying to learn the patterns from the data so that you can predict or extrapolate something in the future for that. And this is generally the way these algorithms work. And that's what you're trying to do. Now, this is a slightly more complex representation of the overall flow, which means that you do pre-processing, you do learning, you do evaluation, and you do prediction. And here you do certain things like model selection, cross-validation, performance tuning, etc. And this is the sort of the overall idea of this within that. So now we come to deep learning algorithms. Again, I'll stop briefly for some questions because this is all still I have done what we have done last time. But if you are doing it, we might as well do this properly. I see some more people waiting here. Okay. Any more questions so far on what I have spoken about the machine learning side before I start the deep learning aspects of it? Okay. Okay, let me see. Okay. Okay. Any
So
questions on this? Yeah, go on.
yeah, one question I want to ask is, doesn't this look like the early stage mathematics that used to exist before 1800, the 18th century? I mean, Leibniz discovered calculus. Newton also discovered calculus. At that time, they had disjoint ideas of how mathematics would go like for the calculus, the differentials, and the integration.
Yeah,
So
yeah,
on. Yeah,
yeah,
this
yeah.
looks exactly.
Yeah, that's actually a very good question. And when I take this session longer in Oxford, I cover this from a mathematical perspective. The short answer to this question is that many of these algorithms, at least the machine learning algorithms, have their origins from history, meaning that if you look at linear regression or logistic regression and things like that, they are functioning in the same way as they function in statistics, and they work in the same sort of a structure with that. What is different about AI, or what is different about their application in AI, is two things. The first one is very easy to understand. The second one is relatively hard to understand. The easy bit to understand is that in machine learning or deep learning, what we are really doing is that we have a lot of data, and therefore the algorithm is then able to extrapolate much better. So you have the big data side and so on and so forth. This allows us to build algorithms which are highly parameterized. So for example, in the y equals to mx plus c equation, we had only two parameters, which are m and c. But when you have a large network which have hundreds of thousands of parameters, and in the case of GPT, you have actually millions or billions of parameters, it is no longer possible to use the statistical techniques to solve such a problem. The second one, and the more complex one, is the way that the statistics is all about trying to understand or explain the model, but it is not so much about extrapolating the model. So the whole point about statistical reasoning is that you do linear regression, you do Bayesian, whatever you do, your main point is to understand the values of the parameters. Machine learning algorithms, and deep learning specifically, deep learning algorithms are black boxes. So black boxes meaning that black boxes meaning what happens with that is they have a very large number of parameters. They cannot explain the parameters, or they cannot identify the values of the parameters, but yet they are able to function so that they can infer something based on the trained model. So when I say the word infer, it means that it is able to learn from the data such that it is able to extrapolate this into a situation which it has not seen before. So the main point, or the main objective of machine learning is inference. So the word inference, and I had this last time, I think, in one of the examples where I showed you the picture of a child learning on a bicycle. And think about it like, if the child is learning to ride his bicycle or her bicycle on a single road, then that child has learned about how this works for that road, how to drive on that road. But the idea, of course, is that they should be able to drive on any other road, correct? So the idea is that they are able to learn from the data so that they can infer this on something which they have not seen before. And this is the beauty of AI, or machine learning. And then the more complicated algorithms they get, the more higher parameters they have. So this is the idea. Okay, does that help?
Thank you.
Okay. Thanks. Okay, there's a question here. Now, when deep learning is developing, is there a need for more traditional algorithm? That's another good question. This is from Rishikesh Pawar. So the question is that do we need traditional algorithm? The answer is yes, because what we do with traditional algorithms is that they are relatively a low-hanging fruit. So it is relatively easier to solve the problem using machine learning or machine learning algorithms than it is to use deep learning algorithms. And this is the generalization, but it is generally true. And the reason why it's true is because deep learning algorithms function quite differently in the way they are building up the data sets, and also they need a lot more data, as I will explain to you in a minute. And for this reason, it is and also, of course, deep learning algorithms work on certain types of data, for example, images and audio and so on and so forth, which you cannot do within traditional machine learning algorithms. So both are quite useful. It depends on the problem you have at hand. Very good. Okay, good. I presume that this is all fine. So I'm now going to start the presentation again. Okay. So I've got foundations. So what I'm doing now is I'm going to present about deep learning. So what we have seen so far, and this is still a recap of the last time, correct? So I covered all this in the 2 hours last time. This time I'm trying to cover this in about 45 minutes, maybe. Yeah. So what I'm going to talk about is, when we talk about deep learning, the idea of deep learning is relatively new. And it is the basic idea is that you are trying to model the human brain using biological neurons. So the idea of neurons is that the neurons are connected to each other, and you take an input neurons and there are hidden layers and there is an output layer. The idea is that you transition across from these neurons, and the neurons learn the pattern of the inputs so that they are able to sort of predict the output when they have not seen before. So right at the beginning, if I just go back a little bit, quite a bit actually. So what I've shown you here is uh, uh, yeah, so this one here is how deep learning works. So this is basically a series of neurons, and it shows you a large number of pictures, and these are the neurons are trained using those pictures. And then these are labeled images, by the way, so it shows what is a dog or a cat here. Then it is trained, and then it is shown a picture which it has not seen before, and it's able to identify based on what it is. Now, that way the neuron is trained here, you can see that the green ones, the connections are formed. On the left hand side, when it is untrained, the connections are not formed. So that's the general idea of training a neuron. Now let's go back here just to show you where we are at. So the thing is that the next time onwards, you're going to do this in code. That's the main reason why I wanted to cover certain things by today, which I still will do. Because the coding bit will be slightly different for people, but then again, we are going to combine people into groups, some of whom will know coding and some of whom will not, and therefore at least together. So if you don't know coding, you'll be thinking about testing it. So that is the whole point. The point here is that you're going to learn by testing. You're going to learn AI. So the question is that how would you test a particular algorithm even if you don't know how it works? And the person who knows the coding is going to know how it works. And this is how you will work together to learn. And this is the basic philosophy with that. And then you have the generative AI, which is slightly different from there. So, by the way, we'll have a 5-minute break in about 20 minutes. I did that last time as well. I think it's a good idea overall. So coming to the idea of deep learning. So the idea of deep learning is, I can explain it here through this one picture here. Yes. So deep learning is a much more different way of learning. So if you think about the problem of chess, correct? The problem of chess was solved by computers relatively early, and there was a famous Deep Blue versus Kasparov, the IBM's Deep Blue algorithm. And Deep Blue won, and this was in 1990s, late 1990s. But the problem of chess is actually very easy for a computer to learn. And the reason for that is because the problem of chess is what is called a finite domain problem. A finite domain problem has a set number of, has a domain which is fixed. So for example, chess has 8 squares by 8 square. Every piece behaves in a predictable way. Therefore, from a computer's point of view, it's a matter of calculating all the permutations, combinations for all possible moves of all possible players. And this then is able to defeat anybody else with that. But the problem on the right hand side is very easy for a child to do, but it's actually impossible for a computer to do. And the reason this problem is hard for a computer is because this is then what is called an infinite domain problem. And problem is very simple, is to identify that that is a dog. Correct. The reason why it's an infinite domain problem is there are many variants around a core theme. So, for example, a dog could be big, it could be small, it could be a puppy, it could be an Alsatian, it could be a Doberman, it could have a collar, it could have long ears, long fur, long short fur, big tail, short tail. It could be sitting, it could be running, it could be swimming, that kind of stuff. So you go on and on and on and on. There is no finite sort of limit to the number of ways you could picture a dogs. And a problem like that is what an infinite domain problem. Actually easy for a child to understand. The child understands that this is a dog, and the reason why the child understands this is a dog is because the child is able to break down the concept of a dog into a series of concepts which are built on top of each other, or series of features which are built on top of each other, whereas the computer is not able to do that. And therefore this then is the significance of what AI is able to do, or deep learning is able to do, and that is the fact that it is able to break a concept down into a series of features, and those features are hierarchical. And that is what I meant to say, that deep learning, the definition of deep learning which I'm using is called automatic feature detection or presentation learning. And what does that mean? Again, I can show you best in an example. Okay, last time I spent far more time on all these things, but this time I'm trying to cover everything within the reasonable time because I still have to cover something which I haven't done so far on this. So this diagram shows you how deep learning works, correct? So what this is these are the series of neurons we talked about. So each layer is built on top of each other layer. To the lowest layer identifies pixels. The one above takes the pixels and identify contours. The one above takes the contours and identify sort of subsections and so on until the last one shows you what the actual thing is. Now, the first time it sees something, it actually shows junk, correct? Because it is not trained. But as it is shown, and the first time you shows this picture, it says this is the car, for example. Then you find the error and you push the error backwards and you continue to feed it images and retrain the structure such that it is able to identify a particular image using that. And in this is what is how deep learning works. This is why you see images like this in deep learning, because the lowest layers of a deep learning neural network, which is the ones you see here, are doing the lowest layer thing, and each layer is feeding on top of each other. And at the higher levels of the image, as you can see here, you see something which looks like a face, correct? So it is building this bottom up, and that is the real power of deep learning. And deep learning, and the beauty of this is that it is actually independent of anything. So this could be an audio, video, sound, anything like this. And it is able to, given enough data and given enough representation of the data or computing, it is able to train all these neurons such that it is able to identify a particular type of an object, whether it's a dog or a car or anything like that. And this is the power of deep learning. From this, you can even do things like self-driving cars, because the concept is still the same, that it is able to learn something. And to me, what it is learning is a function. And this is why in some cases, some people understand the mathematics far better. So I started learning in Oxford. I teach far more on the mathematics side. That's because if you actually understand this idea, what you're trying to do is that is this thing basically, correct? So you have a function. The function in this case is the representation of an image of a woman or a cat or a dog. And given a neural network with enough depth, it is able to identify the picture given enough the object given enough examples of that object. So now the computer can do what the child was able to do. And it is doing it the same way the child was able to do. And the way the child was able to do this was that basically it basically was able to do work bottom up. And what that meant is that it was able to identify the lowest layers and work upwards from each layer to identify what that is. So in the case of a dog, what it would be is fur, sort of whiskers or eyes or a coat or a friendly thing. All these features would add up, and the child would be able to say that this is a dog based on all these features which are connected to each other. So this is a key concept which you have to understand for deep learning to understand that. By the way, this is not about pictures of cats and dogs. This is about tumors. You can do tumors. You can do genomic sequences, that type of stuff. This is why AI is such a powerful mechanism, because it really applies to anything. You feed anything which has got enough data and enough of computing power, and is able to sort of understand it bottom up. Okay, good. So let me now go back here and see if there are any more questions here. Okay, any more questions on this deep learning thing? No? Okay, good. So we have another 15 minutes before we take the break of 5 minutes. So let me now again continue on this same thing. Yes. And I will continue from where I left. and this sort of what we're trying to do is what type of problems can AI solve or deep learning. So when I say I am mostly talking about deep learning algorithms. Yes, the deep learning algorithms, what is common across them is they are basically used in things uh, which require data. Sorry, non-tabular data, correct? So images and things like that. So you have obviously things like gesture recognition, voice biometrics, machine vision, video surveillance, handwriting recognition, natural language processing, and so on. So you have these sort of more complex applications which can be done with that. And then another way to think about AI problems is to think about what they can do. So if we think about domain expert, meaning try to replicate the domain knowledge of a person, that's one way to think about it. Then you can do domain extension, meaning that you can extend a body of knowledge. So for example, the first example is sort of thinking that you can replace a lawyer, for example, the function of a lawyer. The second one is you can think about drug discovery, meaning finding out new types of drugs. You can think about complex planning, which involves trying to understand a task like operations research. You can think about better communication, which means it involves sort of understanding what the communications are like a chatbot. You can think about perception, like autonomous vehicles, digital transformation, enterprise AI, insurance, and things like this. So there are a number of areas, the classic problems, which can be solved. The last one is quite interesting. So when I mean a super long sequences, meaning that you are able to look at very high sequences such as genomic sequences and so on, able to identify something from there with that. So this was where I had left it last time. Yes, so this is where I finished last time. Um, and then the question was, now we are going to start with something else. So we sort of revised that from last time. Any more questions on this so far? No? Good. So what I do now is I will now shift to what I wanted to do this time round. What I will do, okay, sorry, if 90% features match and a 10% doesn't match, whatever dog, okay, that's a very good question again. So this is a probabilistic. So when you do any of the machine learning or a deep learning and stuff like that, it is not a deterministic algorithm, meaning that it can never say if it is 100% a cat or a dog. If it's 90%, then as long as it's acceptable to you, then it's fine. So obviously, when you are trying to detect whether somebody has cancer or not, you obviously want to be understanding the sort of the implications of it with very high accuracy. But in a relatively small thing, 90%, whether it's something with a cat or a dog is a good thing. So that's a good question. Thank you for that. Any more questions on this so far?
Just one
Yeah.
clarification. You used the term, I think, called tabular and non-tabular data.
So in general, deep learning is used for data which is non-tabular, which means it has images and text and things like this, mainly because tabular data
So
has
I'm just trying to clarify, what does tabular data mean and what does non-tabular data mean?
Tabular data means that you have something like a spreadsheet. Yes, that's a tabular data. A non-tabular data is something where you have like an image. So an image is a series of pixels, correct? That's what I mean by tabular and non-tabular. Is that okay?
So does tabular and non-tabular have to do with attributes or just the general scope of variation?
Correct. I mean, it is to do with both, because if you think about tabular data, correct, so automatically you have the attributes built for you already. So if you think about house prices, yes, so if you look at what makes the house price higher, whether it's near a good school, the number of bedrooms, things like that. So these are all your columns which tell you what the attributes are. So the features are already given for you. But in a classic deep learning algorithm, all you would see is number of images, correct? So they wouldn't see what is in those images, and it's up to the algorithm to then work out what those images are. Sorry, what those features are within those images. Yes.
Got it.
Good. Thank you. Good. So there are two more raised hands here. Yes. Who wants to go first?
So One example of non-tabular data is in astrophysics. They utilize deep learning to point out gas giants, exoplanets, or
Yeah.
Earth-like planets based on images from the James Webb Telescope. They're actually doing it.
Yeah, yeah, that's a very good example. There are lots of examples of non-tabular. The best one, like I said, is many of these things where you have images, these images are very complex images, like we just said, like the James Webb and so on and so forth. And when I say complex, they are complex because they are quite vast and they have too many things, and then you have to identify something small within that. So that's one part of it. The other part is actually what is most popular today is just text. Text is non-tabular data. So when you have a lot of text, it actually is an extremely powerful example of what deep learning works, and that's non-tabular as well. So generally, the word tabular and non-tabular has to do with whether it fits in something which looks like an Excel spreadsheet or not. That's how I interpret that. Very good, thank you. The Shinde sir, yes. You raised your hand, yes, Shashikant Shinde? Yeah.
No, no, sir.
Okay,
Clear.
sorry, sorry.
I have a question which yes,
So it's cleared, or do you have a question?
cleared, sir.
Okay, clear. Thank you, sir. Okay. So Chaitanya, Professor Chaitanya, yeah. You're muted, by the way. You've raised your hand, but I don't know. Ah, okay. Yeah, you're unmuted now. Yes, please go on. Yeah.
Yes, sir, it's completely clear. I have one question regarding this metadata, sir,
Uh-huh.
and how we can clarify that tabular and non-tabular data in terms of classification.
Uh, in terms of classification, if you have a tabular data versus non-tabular data, then the algorithm to classify the data is based on what you learned at the target variable. Sorry, what you learned to label the data. So, for example, if you have a data which is saying spam or no spam, so you have a number of transactions. Each transaction or each email, for example, had a number of features. So it might say what the origin is, what the destination is, which country it came from, and so on and so forth. Each of them became features, and then there is a label to this email which says spam or not. And then the more you are able to learn from that, the more you're able to sort of say that it's spam or not. Is that okay?
Yes, sir. Thank you.
Okay, thanks. Yeah. So there's a question here: structured and unstructured data. Structured data can be, yeah. So these are the same words with that. Structured data and unstructured data is the word structured data is a little bit broader. You can have structure within other types of structure rather than tabular, but for now it generally it applies to the same thing with that. Okay, cool. Okay, very good. So let's go back now. And so what we'll do now is we'll take a 5-minute break now, mainly because I don't want to start a new subject and take a 5-minute break in 5 minutes of that. We'll take a small 5-minute break just for a coffee, which is what I did last time as well. So then we've got 1 hour after that to go with this. The most important thing to remember is that if you are here now, this is great, but then the sort of thing which we're going to applies here to the next one as well. So every session is sort of building up on the next one. Cool. Okay. So for now, I'm going to stop presenting. Okay. I will stop presenting. We'll take a 5-minute break and then we'll back after that. Okay. Thank you. Yeah.
Hello, are we talking?
Okay, welcome back. So I'm going to stick to the time as much as we can, mainly because we still have quite a bit to go. But I think we'll be fine. I think I'll just sort of balance this over time. So now I'm going to sort of start what I intended to start um, earlier in the day today. So what we saw before what we saw before was a basic idea of machine learning, correct? And now, and deep learning, we saw what it is. Now we are going to look at some specific deep learning algorithms. So when people say that they are working with AI, they're really working. They need to know 5 or 6 algorithms, and within that, you know almost everything within it. And then the reality is that people specialize in 1 or 2 things most of their life. So, for example, the 6 key algorithms I would say are regression, classification, clustering, and then you have regression, classification, clustering. Then you have some anomaly detection in some cases. Then you have multi-layer perceptrons, and then you might say something like convolution neural networks. So this is what we are going to do at this point. And I wanted to sort of, the theory of this is a little bit complicated, but it will be enough for you to get a handle of what's happening here. And that's the point here. So the first point here is, you can hear me, yes, by the way?
Yes, yes.
Yes. Yeah, good. That's fine. You can see the screen obviously as well. Yeah. So the first point here is that I'll just sort of explain to you how something works, because you're going to look at it in code. So when you actually build everything using a machine learning or a deep learning model, it's mostly as a series of APIs. And they're quite simple in a way. So if you look at TensorFlow library from Python, you really sort of build those neural network layers, and you fit the model and you train the model and you make predictions using that. So this is the general idea with that. And this is generally how the code looks like. And you will go through the code later on in the next session. So I won't go into too much with that. But the idea here is that um, you look at a basic neural network, and you can think about it in terms of mathematics. Again, I go back a little bit to this idea because you can think the whole thing as a matrix multiplication. So you can think about it like your weights are a matrix, your x inputs are another vector, and you do a dot product with that, and you add the biases within that, and you get effectively a dot product, and then you have an activation function and you get an output. And some of these terms are a little bit new to you, but it doesn't matter. But the point about that, it is very simple matrix multiplication, correct? So you take an input, if you can model all these weights and biases within that. Now, what are weights and biases? So that's something which we are going to look into a little bit here, but I can explain it to you in a relatively simple diagram. So each of those neurons are, 1 minute, let me just go through and find out whether I can find something for you with that. Trying to find out a basic picture because we're in the other slide, unfortunately. Here we go. Okay, this is good. So this is what I wanted to show you. So every of those neurons which you saw, the neurons are sort of modeled on the brain, the neurons in the brain. And the neurons in the brain, any brain, are modeled as a series of inputs, and if the inputs are beyond a threshold, when the neuron fires and affects the next neuron. It's a very simple mechanism, but that's how the brain works. And the idea was to model that using artificial means. So if you do that, then what you have is the summation function here, and you have inputs x1, x2, x3, x4. Each of those inputs have weights, w1, w2, w3, and so on. Then you do a summation of xi times wi, and you add the bias functions, which is the number here which is added, and then you pass it through a threshold value and you get an output. So this is the general way a neuron works, and this is the same way an artificial neuron works as well. And then you have a layer of these, and that is why you call it a deep learning neural network. And the formal name for a deep learning neural network is called MLP, which is multi-layer perceptron. The word perceptron means an artificial neuron. So that's generally the way these things work. And this diagram is the same thing, really. So it's the same idea that you have all these neurons together and you have those weights and biases at each neuron, and you're building this bottom up. So far, so good. Yes. So this is the general idea what you do with that. So now if I go back and sort of look into this idea. So the question here is that when I started off doing this, I'm saying to you that each of this whole thing can be represented as a simple dot product of your weights, your inputs, and your biases, and then you get an activation function, you get an output. So that's the general idea with that. And this idea is the same as what you learned in high school. So there is no difference in the dot product, which you saw in the matrix multiplication when you learned it from the beginning with that. Now, the problem here is that it doesn't really fit in with images. Now, images are behaving slightly differently. So if you take an image like that, which is a series of sort of which is a pixel, say the pixels, and you then sort of start to, if you take the whole as a series of, if you just flatten it out and put it in a neural network, then you mix the proximity. You meaning you miss the things which are near to each other. I explained to you why that's important. So what you do then is you effectively combine what is there with these neural networks, and you effectively combine it as a series within that. So what you do is you combine, instead of each layer being connected to the previous layer, each layer is connected to a group of neurons in the previous layer. And this structure starts to behave differently from traditional neural networks in a more efficient way. So what you do then is you create this, which is called a filter, and you slide it over the right, and you continue to do this until you have figured out the whole of the neural network in that direction. So this is how you do image recognition. And the significance of this is that instead of each of the neurons being connected to every neuron in the previous layer, you have each neuron connected to a group of neurons in the previous layer. Why that matters is because in an image, proximity matters. So if I go and look at an image like this, correct? So all of these things are swans, yes, but a swan had a definite set of features, and those features are sort of connected to each other relatively in the certain space. So for example, if I look at an image like this, then if I take this sort of a yellow box, then I say that here there are clouds, and if I move this in the right hand side, the probability of it being cloud is quite high. So similarly, when I come here, I see this as a sunflower, and I move down, it's likely to be a sunflower, another sunflower, and not a picture of a dog, correct? So the idea here is that an image has what is called temporal proximity. Proximity in terms of what is nearby spatial proximity, SPATIAL, spatial, not SPECIAL. So things which are near to each other physically in an image are often related to each other. And if you use this property, then what you do is you then design the neural network such that instead of looking at all these pixels as a series, as a single vector, which you do in a multi-layer perceptron, what you do is you put them in a sequence such that a group of them, then you sort of compress them at each point. Now, therefore, an image and a neural network designed to identify images is called a convolutional neural network, and that neural network looks something like this. So the main difference here is you got an image here, and each of those subsequent layers are mapping to a group in the previous layer. So what you do here is one of those squares is matching to one image, and you continue to sort of shrink it like this. And then you effectively identify the core functions from there, and identify a section of images further. And the right hand side, you can see it's the car or the image or a van or a bicycle within that. So the main difference of a convolution of a convolutional neural network, and this is called convolutional neural network, is the feature detection aspect of it, meaning that the feature detection aspect of it is a neural network which is built on top of other neural networks, and when in doing so, it is able to identify the features of the neural network which are inside that. I'll sort of explain this to you a little bit more, but the significance of this neural network is that the last part of it is a classifier, and the last part of it is a classifier because at this point all it's trying to do is classify this based on that. But the first part of it, all these neural network layers are primarily involved in the job of identifying what makes up this image. Yes, so this is why I use the definition of convolutional neural networks as representation learning, because the primary differentiator here is not the classifier, which is at the right hand side, but the fact that it is able to pick up all these features by reading, by sort of understanding what they are by this neural network mechanism. Okay, so I will now take some questions before I go ahead a little bit, because this is slightly different from there. But the main point I'm trying to remember, the main point I'm trying to tell you is that if you think about the idea of the multi-layer perceptron, the idea of the multi-layer perceptron was that you took a neural network, you took a problem, and you flattened it such that you then fed it into a neural network. But in the case of a convolutional neural network with images, you don't flatten it, rather you use it as it is, so that it is able to build up and pick up features of an image based on the idea of the convolution operation, which means that you go through a particular section of the image and you go and identify um, things which are relevant in the image. Okay, so any more questions at this point? This is slightly different, but the theory of convolutional neural networks is something you need to understand, because many of the problems of deep learning are effectively image-based problems with that. And of course, you will see this in code in the next session. That's why I'm talking to you now about this, so that you are able to understand the basics with it.
So I just had a network glitch because of which I got dropped. But one question I had was, you're talking about the image data and the local connection of the network, but the image data basically is just things like an array of your RGB values, right?
Correct, absolutely. Yeah.
Yeah. So when you take that RGB values, I mean, it's like a matrix of RGB
Uh-huh,
values,
uh-huh,
and you have to identify certain regions that are
uh-huh.
important. So are
Yes.
you just talking about identification of gradients and then processing the gradients, or are you talking about something else?
Okay, I will come back to this in the immediately after this, because it is easy for me to show it to you in an image rather
Okay.
than talking about it. But yes, that is a very good question. I'll come back to it in a minute. Okay, any more
Thank you.
questions on this so far? Thanks. Yeah. Okay, so far so good. Again, remember that people look at it in different ways. So the first time you look at it might be different, but people generally understand it into different things. So for example, some people might um, understand it from images, or they might understand it from the maths, or they might understand it from code. But it doesn't matter. I mean, whichever way you understand it, that works quite well with that. Okay, so now I'm going to go back to the slides here, which were here. Yes. So now I'm going to effectively come to the same question which was asked by Kedar a minute ago, was how exactly does this work from first principles? So what happens essentially is that what you must understand is how do filters work, correct? So this thing is called a filter. This thing which slides across the image is called a filter. Yeah. So what happens is, if you have an image like this, then what is happening is it starts from the top left hand side and goes through all the image, and then identifies each of the subsections, and then the whole thing goes through across the deep neural networks and trying to learn from there. So the way this works is that if you look at an image like that, which is an RGB image in this case, and what we see is the dog, but the computer sees this. By the way, these are not random numbers. They are higher or lower depending on the intensity of the image. So this is a particular structure of the image with that. But the point here is that all the computer is seeing is a matrix within there. Now, if I look at this particular curve here, yes, so this curve can be represented as a series of zeros all over, but in the middle there are these 30s, because that represents the sort of the density of the black line, which shows you this image which has gone in this way. Yes, so far so good. So the question then is, if this is the filter, that means I'm trying to identify this particular object, this particular representation in the image. How does this work? So if I have this image here, and this one, remember now, is this curve here. So if this one is the right hand side one here, then this is sort of all these 30s here with that. So that represents the line. And if it is then at this portion of the mouse where this actually is present, correct? So this is actually present in here because this curve is the same one here. So when I go here and slide it over this point of the mouse, what I do is I multiply non-zero numbers and I get a number which is quite large, correct? Because you don't have zeros here in the 30s and so on, and nor do you have the zeros here. So you multiply these two things with a dot product as you did last time, and then you get something which is larger. Yes. Now, if I slide this image here where the mouse's ear is, so the matrix here on the right hand side is still the same one as before because you have got the numbers here, but this one here has got zeros here. So when I multiply these two things, I get a zero. And the reason I get a zero is because this particular feature, it is looking for this curve here on the right hand side, the same curve as what we had here, actually does not exist in here. So when I multiply these numbers like I did last time here, I got a bigger number, but when I multiply these numbers here, I get a zero. And the problem here is that it's not a problem, but the fact is that when you multiply these numbers, you get a zero. That means it shows you that this particular feature is absent at that part of the image. So this is what is the meaning of that, and that is what you mean by each of these being effectively filters. So what happens is this whole operation is a series of sort of filtering operations and what is called a convolution operation, which effectively scans through the whole image and finds out things which are relevant in those images, and then effectively represents them at the neural network at that point. And this is what you end up doing with this, and that's the general way with that. So the sort of an important point here is a convolutional network, the simple neural network that use convolution in place of a general matrix multiplication in at least one of their layers. So what it means is that in traditional neural network, you have a matrix multiplication, but in a convolution neural network, you have a convolution operation. The convolution operation is nothing but another matrix multiplication, but the one of the matrices you are multiplying is a small one, and it represents what is effectively a feature you are trying to detect in the image, and that's what it is really. Okay, good. Any more questions on this so far? So this is basically why I said that. Yeah.
One simple question on that convolution. So you said that the filter is going to depend on the feature you're trying to recognize, right? So the choice of filters is based on some other algorithm, right? It's not detecting just, for example, if I wanted to detect some boundaries of the regions,
Yeah.
that you could do without a filter by just processing the RGB data. That's not what you're talking about.
Correct. I'm not talking about the boundaries. I'm talking about what is there in the feature as represented by an object of interest, which represents the image. So, for example, if it is a cat, then whiskers is a feature for the cat. Yes. So that's what I'm trying to say with that. But for a computer, it's all numbers, correct? So computer doesn't know that it's a whisker or a paw or a fur or anything like that. It is simply a large sort of a pattern recognition exercise done over and over again, such that it is able to discern a particular pattern and then build up a hierarchy of those patterns, given enough examples of that feature.
Okay, so can I ask, this is more of an academic question, maybe, if this is not the right place, but I want to ask the question. Let's take the example of just a 0-1 function, which is 0 everywhere except between the interval 0 and 1. If you do the self-convolution of that step, you're going to get a spike. That is a recognition with available data. Whereas what you're talking about is, if you wanted to recognize whether there are sharp steps, then you're going to get the graph and do convolution with a predefined notion of the step to see whether that kind of step exists. These are two different operations, correct?
Yes. So I'm not talking about self-convolutions. I'm talking about the second one.
Okay, got it. Thank you.
Yeah. Thanks. Yeah. Good. Thank you. Any more questions on this so far? Because I know this is slightly different, and I think this is something which it's good if you understand it, because then when you look at core, it will make a bit more sense to you. Because the code actually is quite easy in a way. I mean, if you understand code, correct? Because what that means is that you are just calling an API, and you're calling the API in a certain way, and hopefully that just gives you an answer if you have the right data. Yeah. Any thoughts? Any questions? Yes. Yes. No. Okay. Good. So what I'll do now is I will continue the discussion, and let me just see where we are at. Okay. Okay, so where we were here was that we were doing this thing here, and we talked about these images, and then there are sort of other things with that. And this is just sort of explaining what those layers are in a convolutional neural network. You can read through that and sort of go through that quite easily, and that should be quite okay. Yes, but the main thing to remember that the convolutional neural, the primary difference is the convolution operation. The convolution operation is that thing with the filter stuff, where it tries to find out sub images in the image, sorry, sub features in the image, and then work through that within there. Okay, now I wanted to look at one final thing. No, sorry. So this thing, just a recap on the previous time, and now you understand this more because you sort of look at an artificial neuron and understand how it works, and then understand. And now you also understand what I mean by deep learning as a representation learning. Because in traditional machine learning idea, you actually have to have all the features. In a deep learning algorithm, you don't have this step of trying to identify or know those features in advance. Rather, you just feed all the data to the algorithm and it does all this thing for you. Now, obviously, there's a cost to doing that. When I say cost, I mean complexity, time, GPU processing power, etc., etc. So all these things are not easy to achieve, but nevertheless, they are possible depending on the type of problem you have with that. The other bit is that these are better solved at nonlinear problems. So a linear problem is a relatively easy one to solve. So a linear algorithm basically tries to find the best fitting line across a series of points. A nonlinear algorithm tries to find out, it has a pattern which is far more harder to understand, as in you have a pattern here, and sort of what you do is uh, this pattern on the right hand side is relatively harder to understand because it's not a straight line. However, a pattern does exist because the circle separates the blue circles from the green circles. So nonlinear patterns are much more harder to understand. A deep neural network is a way to understand nonlinear problems. Yes. The final point, which we are going to talk about, but we won't do this in code, is what is called temporal problems. Temporal problems depend on time, as the word implies. Yes. So temporal problem means that you have something like recurrent neural networks, LSTMs. And the idea here is that you are looking at a neural network by considering the input of the previous one. So a traditional neural network always takes in data, like for example, x of time t and x of time t plus 1 and x of time t minus 1. So this is the way you would take it for a temporal neural network. By this I mean that you take the data from the previous step. So you take the history, because a traditional neural network does not have a history, because you just take a particular image at a point in time. But if you take the historical data, then you get a different type of a neural network called LSTM, which we won't go into too much detail, but it is an important one to know overall. It's a little bit more a complex architecture from there. There are some videos here at the end of it if you are interested, and you can find out more about this as well. Okay, so now any more quick questions before I slightly shift the goal here and try to show you something else? Any more questions on this so far? So again, we have covered quite a bit, as you can imagine. Okay, sorry, somebody's raised their hand. Yes, please, Professor Chaitanya. Yes, please go on. You're muted. Okay, I don't hear you, but maybe your hand was raised.
Sir,
Yeah,
yeah, yeah.
now I can
Hello.
hear you. Go on. Yeah.
Sir, my question is regarding this feature selection and feature extraction in CNN.
Right.
Similarly, as you said in last selection of our filter is depends on that algorithms. So
Mhm.
definitely the feature extractions in case of large volume of data. How you select the appropriate features and these attributes of that.
Okay, this I will share you with another paper, which is best explained by looking at a paper. So I'll share that with you into paper, and then we can discuss next time. Okay.
Okay, sir. Thank you,
Okay,
sir.
thanks. Yeah. So there are two more questions here on the chat. So difference between convolution matrix and the other matrix. So convolution matrix and normal matrix are just matrix multiplications. The main difference in the convolutional neural network is that the convolution operation is is a smaller matrix, and it represents something, in this case a particular feature which you think exists in the image. That's the main difference between that. And the question is, um, when there are large number in the large number in deep learning, there isn't a possibility model to get confused and give false results. So it's not a question of confused, it's the question that it is hard to train such a model, because when you have a very large number of parameters, you also need a very large amount of data to train it. So I think that if you have the data, you can train the model, but you do not have the data, then I think it will be harder to train that. So that's the sort of answer to that. The CNN model versus GAN model, I think you mean GAN. So GAN is a slightly different thing, which I sort of touched in the last session. A GAN is a model called a generative adversarial network, and it works in a way in which you think about a sort of what is called cops and robbers. So you have somebody creating fakes and somebody trying to see if the fakes are good or not, and until such time that the creator of the fakes is so good that they're able to create a good fake, which is almost as good as the real one. So the main example of GANs at the moment is things like deep fakes and so on and so forth. So generally that's what you see within a GAN. So that's the main difference with that. Okay, good. So let me just see if there is no other hands. Okay, there are no other hands. Okay, any more questions before I switch something? Okay, so now I'm going to switch this what I am representing here, and I'm going to show you something different. Let me just see what I have here. It will take me a couple of minutes to do this. I will shut this down. So I have too many windows open. Um, okay, so I am now going to share with you a particular notebook. Okay, so this document, I'm going to share again now my screen. So I'm going to start sharing my screen. Okay, so this particular thing is something from Amazon. Yeah, I really liked it very much because it's a very visual way of representing algorithms. And it also represents some things which I wanted to talk to you about, but I think it's better that my goal was in this session that I sort of have you guys work in groups and present things to each other, but that isn't possible. So what I'm going to do is I'm going to look at some of these ones, and some of the rest of them we will look at in the next time. But this link is there in the notes which I have shared, is notes with today's date, and what it shows you is all these sort of things which are best learned visually. You can understand them visually. So let's start with linear regression. So linear regression, is basically, it sort of says what linear regression is. It talks about these things, then how it works. So what it does is you effectively start off looking at the size of a house. It takes the house price example, then it finds out these residuals, meaning you plot these different points and find out the error or difference between that and the point which you want. Then you shift the line. When you try to shift the line such that you try to find the best fitting points, as you can see, to here we started off like this, trying to find a flat line first. You started off with something, then you continue to fit this example with the errors and try to reduce the errors such that it fit this way, such that here you had the maximum number of points, and that is what you continue to do. You continue to find the sort of a particular price of a house by square feet and the house price. So this is a particular feature, size and the price, and you continue to sort of build this idea such that you can sort of learn from there. And the question is, how do you evaluate such a model? And as I said to you, that the mean squared error is the error for model evaluation, and then you sort of understand how this works. So for example, if you shuffle the data using some of these parameters, I think this works like that. Yeah. So what you are seeing here is how this changes depends on these parameters, and you can sort of have a look at them as you develop them. But I think that's the best way to explain some of that, and given enough examples through each of those steps, as you see, for example, if I do this with one step, it just moves like that. 25 steps, it moves like that. With 100 steps, it has moved like that. So what you're seeing here is that you train it with a series of steps, and it fits in what looks to be the best possible line in this case, by minimizing the best squared fitted line from there onwards. And now then there are some more examples of this which are a bit more complex. For example, you've got multivariate regression. You got regression with interaction, continuous features, and so on and so forth. So the point here is that this is a sort of a good way for you to understand some of these ideas, and it's also with visual. So I suggested you have a look at this. So this is one of the first ones I wanted you to see. The second one, so don't look at reinforcement learning. That's a little bit more complex algorithm. Second one is test, train, and validation sets. So like I said, what you do here is you have the data splitting. So you have a test data set and you have a train data set, and you effectively split the test, train, and validation data set, and the training data set is what you use to learn the model. The testing data set is used what to sort of test the model, and then the validation data set is used for the hyperparameters within that. So you start training the model with that, and then you build the model with certain examples. In this case, you're trying to classify the two types of cats, well, cats and dogs, yes. Then you do the validation set where you train it, where you test it against that. And then you do the test set where you test against the hyperparameters with that. So the point here is that I would like you to have a look at this in your free time so that you can understand how this works. There is no code here, but it is a very good visual representation of what's going on with that. The third one I would like you to see is what is called this is a random forest model. Okay, decision tree, that's a good one. So decision trees are ways in which you sort of split something. So you have a root node, you start off with something like that. You're trying to sort of split the categories, and you start to find out what it is, find out the decision boundary, and you split across that, and you keep on making smaller and smaller splits until you see the sort of the categorization within that. So again, it's a good and a very visual way to understand something, which would be sort of easy for you to understand, um, based on the sort of understanding of the visual stuff. Then the next one is the next one is The next one I would suggest is you look at uh, cross validation. So cross validation is something which shows you how you can validate something. You have the data, you split it into test, train, and train, test, validation, and train, as we have seen before. You do something called k-fold cross validation, which means you instead of splitting it across test, validation, and train, you do it in small segments, and they effectively train it across different segments with that. So again, it's well worth to read this with test, train, and validation sets with that, because we'll be doing this in code, so it's worthwhile understanding what this is. Yeah. Now the next and I think the last one is yeah. So logistic regression is a classifier. So this is another good way to learn something here. So the classifier, how it works, again, you're trying to find out if it's a sunny day or a rainy day based on the temperature and the probability. So this is how you sort of work with that. Um, and you estimate the coefficients of this variable within this. So this is good. Yeah. And worthwhile. And the final one to look at is what is called ROC, which is uh, a receiver operator characteristics. And again, it's a way in which you look at false positives and things like this within that. So again, worthwhile looking at this bit visually as it goes through. You can see how these things work with that. Okay, good. So what I wanted you to do was to sort of look at these and read them up over the week, at least get a basic idea of how these things work, so that when you come to code, it will be easier for you to understand that. So I don't expect you to know all of it, and this is exactly why I said to you that in AI or machine learning, you will not understand all of it, but it's important to understand enough so that you can work with something, and that working with something effectively is what we are going to do in code, and then later on in the whole different area of convolution, sort of uh, the uh, the chat GPT type things um, with that. Okay, good. Any more questions on this so far?
Just one question.
Yeah.
The per session notes and the links, they are posted and shared with everyone on a Google Drive, right?
Yes, I will share this thing with you again. It's the same one I shared before. Let me first stop sharing my own screen so that I don't stop presenting. So I'll go through this again because it's important for people, especially some people didn't come the first time round. So I will show you, I will share this thing again. So the link for this, I will put it in the chat. Okay. So this link, which I'm putting in the chat, is where everything is. And so this is the shared drive. I'm again going to share my own screen so that I can show you what's in the shared drive. So in the shared drive, what you're seeing is what you're seeing here is this note, this document I shared with you. Notes is where that thing I showed you just now, the visual stuff is. It's just one link there with that. So this link here is got this one document here, which shows you what we just saw. Then these are the notes from so sort of these were the foundation ones from the first session. So these two are from the second session. So this one I have not yet done, the evaluation metrics I haven't done, which I will do right now. And this one was all the other notes I had. So we had keywords, we had the gherkins, which we're going to do, and then you had some more documents here within that. Similarly, in the foundations document, uh, it had also links to other things. So by the way, let me just check what this is. Yeah, so you have model evaluation, machine learning, some more concepts here. and so on. So in the model, in this document here, the first document, 1 minute, let me just see what this document was. So this one here, which I shared with you in the beginning, this has this link here is what I also wanted you to see. So this is a free book, which is very good. This by Jake Vanderplas, and this is a glossary. It comes from Google. It's probably the best glossary on the internet which I have seen. And other references are the references I have already shared with you with that. But everything is there sitting here in the drive, in the same drive, including the slides from today. The last thing which I want to quickly share, is that okay? Yes?
Yes, that's good. Thank
Okay,
you.
good. Yeah.
Yes.
So now I just, because I know people weren't there last time, so just to be sort of recap that. So the last thing I want to share with you is this thing, which is model evaluation. So this small slide, which is actually by my colleague called Marina, who is also from Oxford. And you can see my screen, yes?
Yes.
Yeah. So
Yes.
this one is really all these evaluation metrics, but they're put together in the same way, in a simple way. So you have sort of reading the pre-processing, training in the model. So this is the overall flow. And there are certain things here which you have to do. So for example, look at the missing data, look at feature extraction, look at feature engineering, feature scaling, etc. When you train the model, you do cross-validation performance metrics, and then you do parameter optimization, and then you do the final model evaluation. That's a general flow. And then sort of classification and regression has certain sort of metrics with that. Why is this not moving? Yeah. And then you have effectively what is the loss function and evaluation metrics to do, and then you have effectively how you do the hyperparameters. So hyperparameters are parameters which are not connected to the model itself, sorry, not connected to the data, but they are set overall. So for example, if you have the number of layers in the neural network, that's a hyperparameter. So things like that. So then there are certain ways to find out these hyperparameters, and then these are the listing of the regression metrics. And some of these, again, you will see these in the code, so don't worry too much about it. It's just listing. And these are the sort of classification metrics. With that, the regression metrics, the classification metrics. We have called confusion metrics, and all these things: true positive, accuracy, true negative, and so on. And then which ones to choose. Some more ideas for that with that. And then you look at sort of evaluation metrics, you compare them with that. Okay, so that covers everything which I wanted to cover more or less today. And the idea here is that you will see this in code the next time, and this is exactly why we kind of, it's easier to see, just have a look at them over this week, and then we'll discuss this next time around in the code. Okay, there's a question here. So Professor Chaitanya. Yeah, or maybe you raised your hand before. I don't know. Maybe it was from before. Okay. So any more questions now? Okay. So I'll just quickly recap what we have done so far. Yes. What we have done is that we basically went through and looked at what are machine learning algorithms, what are deep learning algorithms. Then we went through and what convolution neural networks, and then we look at evaluation metrics. So these are the four things which we have sort of started to look into overall the flow of machine learning and deep learning, and that's sort of the way you kind of understand how things work. And the main thing is that you then are effectively looking at you then are effectively looking at something which you can implement in code, and this is what we are trying to get to over a point in time. Okay, all right. So if there are no more questions, we can stop here today. It's about 15 minutes early, but I think it's well worth to stop it at a certain point in time, and the rest we can discuss it next time. Any more questions for now?
We're going to talk about Chat GPT. How is that related to this course?
Right. Yeah. So what we're talking about here is that there is a new workflow effectively, which is coming through what is called generative AI. And generative AI, the best example of that is ChatGPT, but it is actually a bigger thing. OpenAI has a platform called GPT-3, and that's how it works. So effectively, that's a workflow in which you are able to combine a model which generates data for you, and there's particular type of applications which work with that. So these are effective discriminative models, and the generative models are what we're going to do in the later part. Is that okay? Okay, good. So basically just another type of model. Yeah, thanks. Okay, any more questions? Okay, good. Thank you. Then we'll stop for now and we'll see each other again next week. Thanks. Yeah. Okay. Thank you.
Thank you.
Thank you.
Thank you.